Check this out. We've got something really fun today. This is so amazing. Oh man, again?
1.7 Infinite series. A series is the sum of terms from a sequence. They can be finite, but we're going to be interested in infinite series. Infinite series can be convergent, so as we add more and more terms, they get closer and closer to a value. They can also be divergent. As we add more and more terms, they diverge to positive or negative infinity. This is called sigma notation, and it's named after the capital Greek letter sigma. So let's look at an example of how sigma notation works. So we write our sigma here, and below the sigma, we would declare our variable that we're counting. So I'll use n here, and then we give it a starting value. So I'll say this one starts at 2. It's going to step up by 1 each time until it gets to the maximum value up here. So I'll just say this one ends at 5. And for my example, I'll say that our formula is n squared. So that means the first term is n equals 2. So it would be 2 squared. And then we add 1 to n. So the next one would be 3 squared. And then 4 squared. And finally 5 squared. And that's where we end because 5 is our maximum here. So these ones here say that n starts off at 1 and then go all the way to infinity. And so we'd be adding term 1, term 2, term 3 forever. Now we need to determine if these series are convergent or divergent. So if you can't immediately tell by looking at them, then try writing out some of the series and look for a pattern. So S1 would just be 1. S2 here would be the sum of the first two terms here, so negative 1. S3, we're going to add 3, so that would be 2. S4, we're going to add a minus 4 to this sum, so that would be negative 2. S5, looks like we're going to be adding 5 to this, so that would be 3, and so on. I think we have enough to recognize a pattern here. It's not a pattern that is getting closer and closer to a specific value, so we call this one divergent. Let's look at the next one. S1 would be 10, S2 would be 15, S3 would be 17.5, and S4 would be, adding this, 18.75. I think that's enough to see that although we're increasing less and less each time, so we're going to eventually get closer and closer to a specific value. So this one is convergent. In this course, we're going to work with infinite geometric series, but first let's develop the formula for geometric series. And here is our series. S is equal to, instead of T1, we're going to use A as our first term. Now we're going to take this equation here and multiply it by the common ratio to get this equation. So every term is being multiplied by R. And then we're going to subtract the two equations. So on this side we have S minus S times R, but on this side we have a bunch of things that will cancel. The AR minus the AR will cancel out. AR squared minus AR squared will cancel out. You notice we're canceling things out diagonally like this, so that when we get to the end, we're just left with this term here. So that's why all of a sudden we only have two terms on the right-hand side, A minus A times R to the power of n. Now there's a couple of things we can factor out. We can factor out the S on the left and the A on the right, and then divide both sides by 1 minus R to solve for S. Now this is our equation for geometric series, but we're really interested in infinite geometric series. And there's two things that can happen. If R is greater than 1, or the absolute value of R is greater than 1, then this term right here goes off to positive or negative infinity, which means that the limit of this series does not exist. And that's all we can say about that. But there is something we can say about these ones. If the absolute value of R is less than 1, then right here we would have the limit as n approaches infinity of just this portion of our formula, r to the power of n, this will go to approach 0. And that means that this part of our equation just becomes 1 minus 0, which is just 1. And so in the numerator, we just have a. And so the limit of our series as n approaches infinity is a over 1 minus r. Or in 20-1, we also wrote this as t1 over 1 minus r. We want to find the sum of these infinite series if they exist. So we have our infinite series is equal to our first term over 1 minus the common ratio. The common ratio is found by taking a term and dividing by its preceding term. So let's do 9 divided by negative 12. We can simplify this to be negative 3 over 4. So I'll put it in brackets, negative 3 over 4, but if you want to just put plus 3/4 right there, that would be fine. I'll do it in 2 steps. Now I've got 16 over 7/4, and I'm dividing by a fraction, so I'm going to multiply by the reciprocal. And that gives me 64 over 7. This one here, our infinite sum, is equal to the first term, 1 minus, and this one's pretty easy. 1 divided by 4 is just 1/4, so 1/4 is our r value. Now we have 4 over 1 minus a quarter is 3/4. And same as before, I'll multiply by the reciprocal, and I'll get 16/3. Same with the next one. Give it a try. Unpause the video when you have the answer. So our sum here is our first term. And then we find our r, and it's negative 3 over 2. But the absolute value of this is greater than 1. So that means that our sum does not exist. Careful with this, because if you actually tried it, it looks like it's going to give you an answer. So if you put in all of this information, it will give you some answer, but really the r value is greater than 1, or the absolute value of the r value is greater than 1, so this sum does not exist. If the overall dimensions of the square are 8 centimeters by 8 centimeters, what is the area of the black squares? You can see them going off there. And we can suppose that that's an infinite process there. So the area of this first one here would be 4 times 4, and so it would be 16. The area of this one here would be 2 times 2, so it would be 4. The area of this one would be 1 by 1, so it would be 1. I think that's enough to see the pattern here. So our infinite sum is equal to 16 as our first term, and 1 minus, we can take 1 divided by 4 would be our common ratio. 16 over 3/4, and 16 times the reciprocal gives me 64 over 3, and we're doing area, so centimeters squared. Now in this case, we didn't actually need infinite series. It looks like each time we cut this into 3 pieces, one of them is shaded black. So we need 1/3 of the overall area. The overall area would have been 8 times 8 is 64, so 1/3 of that is just 1/3 of 64. A ball falls off a table 2 meters tall and bounces infinitely many times, which with each successive bounce, it bounces 3/4 of the last bounce's height. And how far will the ball travel vertically? So I'm going to do this question a few different ways. You should probably pause the video and restart the video once you have an answer. So option 1, you notice that this isn't very nice. This has got a down movement, and then a down movement, and a down, and a down, and a down. But it also has an up movement to it. So this is an up movement, up, 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 and we need to count this all, and we can't count it together as one series because there's a single term here and then there's 2 identical terms here and here. So that's the issue that we need to get around. So option 1 would be, forget about this initial bounce. Let's just say distance is equal to 2. That would be our initial bounce. And then make the rest of this into a series. And they'd be 2 identical series here. One in the green for the up movements and one for the down blue movements here. And this, again, is for the initial 2-meter drop that doesn't really fit into the rest of this pattern. So 2 plus, and then this is 2 because there's the up and down, so 2 times. Our next movement here would be 3/4 of 2. So 3/4 of 2, which would be 3/2. So our starting term for our infinite series would be 3/2. And then it's 1 minus 3/4, because 3/4 is our common ratio. There. Now we can just calculate this. We get 3/2 over 1/4, and then multiply by the reciprocal. So 3/2 times 4 is 12/2, which is 6. And we got 2 times 6 is 12, plus 2 is 14 meters. That was the first way, and you may have done it that way. But let's do it another way, just so we can analyze this problem a bit more. So option 2. Let's say that we just imagined there was an up movement here, and that way we could do all of this with 2 identical series, but then just subtract off the extra 2 that wasn't really here. So this distance would be 2 infinite series, and then we're going to minus off this 2 here that wasn't really here. So 2 times. Now this, if we did it this way, our initial term is 2. And then it's still 1 minus 3/4 in the denominator. And we need to subtract off 2 because this dotted one isn't actually here, but we're counting it in here. All right, and then we can just work with this. So this is 2/4. And then this would be 8. So this would be 2 times 8 minus 2 would be 16 minus 2, so 14 meters. And of course we got the same answer because we're doing the math right. Let's do one more option, and I'd be interested if you did it an even different way than these 3 options that I'm covering here. Let me know. So our distance is equal to, we could just simply split these up into the blue down movements and the green up movements. So our blue infinite series and our green infinite series. So the first infinite series would start at 2, and the second infinite series would start here at 3/2. And then we'll just add them up separately. So this one would be 2/4, and this one would be 3/2/4, and this will be 8, and this will be 6, and that still gives us the right answer. Another application of infinite series would be writing a repeating decimal as a fraction. Now, for me, really, I hate this repeating decimal. I think it's misleading, and so any way to get it to a fraction will be great. So first, let's break it up. Here's a 2 out front, and that's not part of the pattern, so I'm just going to separate that. Next, it's 90, so I'm going to write 0.90 plus 0.00, and then 90 again, because that would be the pattern, and then plus 0.40, and then 90 again, and so on. And these create an infinite series, not this 2 here. It's just extra, so I'm going to leave it out. So 2 plus, here's my first term, is 0.9, and I like fractions a bit better, so I'm going to write 9/10. Now it's 1 minus the common ratio, and each time we're going to multiply by 0.01 or 1/100. Keep the 2 there, and we got 9/10 in the numerator, and we've got 99/100 in the denominator. And now we can simplify this we've got a 9 here, and that can simplify with 99 here, so we'll get rid of both of those, and this will be 11. And then we've got a 10 here, and that will get rid of one of the 10s here. So I know we cross that a lot. Maybe do this in more than one step if you get confused, but this is 1 over 1, or just 1 in the numerator, over 11 over 10. So if we were going to multiply by the reciprocal, this would turn into 10 over 11. And now we could change this into a mixed fraction here, so 22 plus 10 is 32 elevenths. Try the next one here, get an answer, and then restart the video once you have your own answer. This 1.3 is not part of the pattern, so we're going to break it off. And then the rest of the pattern proceeds like 0.08 plus 0.008 plus 0.0008, and so on. So the 1.3 here is just going to stay 1.3 for a while, but the rest of this make up our series. Our first term is 0.08, and this time the common multiplier is 0.1, or 1 over 10. Now I'm going to change everything into fractions because I find they're easier to work with. So this would be 13 over 10, and this is 8 over 100. And this is 9 over 10. And we can start to simplify from here, 13 over 10. This 10 will cancel out with part of this, and that would be good. And also we could divide numerator here by 2. So this will be 4, and this would be 5. Now let's do one more step, just because this is kind of messy. We got 4 over 5 divided by 9. And let's say 4 over 5 times the reciprocal is 1 over 9. So we've got 13 over 10 plus 4 over 45. And we need a common denominator here, so it looks like 90. So multiply this by 9. So we'll get 117 over 90, plus this one be multiplied by 2, so 8 over 90. And then finally 8 plus 117 is 125 over 90. And then we see, hey, this is divisible by 5, so that would be 25 over 18. And then finally, we have our nice answer in simplified fractional form. After this lesson, you should be able to determine if a series will diverge or converge, and you can find the limit of a series if it converges. Here's some questions from the textbook. Give them a try, see if you know what you're doing.